compare and contrast. I want to compare and contrast. So for a single average, the t-score that we've been calculating, and I've only made you calculate these a small handful of times, and when I say small handful, I mean like once or twice. You calculate these bad boys by taking your sample average and figuring out how far it is away from your assumed population average. That's your difference. And then what do you have to divide by? What have we been dividing by all term? Good! Very nice! Very nice! S over the root of n, if you don't mind, Aaron, just because we have to tie the variation into it. Somebody was going to say standard error, I almost thought, or standard deviation. That was correct. Whoever was going to say that, that was correct. You have to measure this difference by dividing by a standard deviation. Is 2 feet meaningful? Is 2 feet a meaningful difference? What's the best way to answer that question?
We don't know. Depends.
Good. We don't know because it depends. It depends on how widely varied the data is. 2 feet might be a meaningless difference if the standard deviation is 4 feet. But it might be a hugely significant difference if it's only an inch. 2 feet, if the standard deviation is an inch, is 24 standard deviations. That's meaningful, isn't it? But 2 feet, if the standard deviation is 4 feet, is a half a standard deviation, which is meaningless. So it all depends on this. It all depends on this. Cool so far? Okay, so this is what we just got done doing, essentially, or what we've been doing with a single t, whether it was an interval or whether it was a test. Now we've got to go to 2 averages. How do we deal with it? Well, as it turns out, it's not that much of a big deal. You simply expand what you know for 1 to make 2. So for example, we don't have 1x bar anymore. We have 2 of them. So look at the difference of those. Order's irrelevant because the samples are independent. You should keep track of which one is which because the test statistic will give you an indication of which one's bigger than the other one. Now, technically speaking, ask me that question, Brian. Ask me that question.
Well, I'm just thinking if we're subtracting a negative plus, it's not going to have any reference.
It will. That's why I said the t-value will tell you something about which one is bigger than the other. We'll come back to that when we look at our data. Now, technically speaking, when I put this in orange, there should also be a mu reference over here. I'm putting that in orange, though, because most of the time we ignore that. Because what do we assume about these 2 averages if there's no difference in the breaks at all? That they equal each other, which means the numerical value of this is going to be 0, which means this whole part just disappears. Most statisticians don't even make reference to this anymore. Technically speaking, it's there because it's a part of this. But the difference is, just like it was for matched pairs, is that this was 0, that'll be 0 too. So I just put it there because there is a corollary to the old t-score. It's not like it just disappears. It's just mathematically it disappears because usually there's a set difference of 0 assumed. Is that fair? Now here's where it gets interesting. What do we divide by? What do we divide by? Well, in general, what do we divide by? Give it a name. The standard error. Exactly. So what is the standard error when you have 2 samples? I have a list of my 5 favorite problems in statistics that I've had to work through on my own. This is definitely in the top 5. Because it's one of those things my profs would tell me. Oh, it's this, Sean. Blah, blah, blah. Why? That doesn't make any sense. Because it is. That doesn't make any sense. Okay. Are you going to make it make sense? Walk away. Okay, I'll go home and prove myself. So I went home and I worked through it myself and I said, son of a bitch, it does make sense when you play with it algebraically. But rather than playing with it algebraically, I designed a spreadsheet for you guys. This is my default go-to instead of algebra for you, instead of filling with more with algebra. If you want the algebra, it's on the enrichment page. I proudly have it there for you guys to examine. There's some fun algebra behind it. For those of you that can't stand algebra, see if you can buy this.
Wouldn't you still have the same standard deviation?
But you have to view them both together. They now have a combined standard error because you're subtracting the 2 variables of the average of the cantilevers and the average of the V-brakes. So because you're subtracting them, they aren't the same anymore. Chris, it's a very good point. So one way of dealing with it, of course, would just be to subtract the variances, right? So if this is a single one, you might say to yourself, okay, well, let's do S1 over root N1 minus S2 over root N2. Right? This is the, if you will, for the V break standard error, that's the cantilever break, just subtract it, right? That makes perfectly logical sense, doesn't it? You're subtracting the averages, why not subtract the standard deviations?
It's not gonna be that easy.
Why?
Because the numbers
Because
are
you're,
different.
Well, that's okay. I can live with that. I can live with that. The numbers are different. I can live with that.
No, I mean, like, the reference of the average, I mean,
Good.
you have a large or a small sequence.
That's a fantastic statistical idea. I was going to give you a much simpler mathematical idea. It turns out very often when you're doing inferential statistics that these two numbers are very close to each other. And it also turns out, and when you control studies, that the sample sizes, although not always equal, are close to each other. So if these are close and these are close, what's this going to be equal to?
0.
And that's a problem. You can't have zero standard error. That doesn't make any sense, right? If each one has standard error, you can't lose all that error and say like, well, Brandon over here, he screws up measurements by ½ an inch, and Sean screws up measurements by ½ an inch. That's a wash. You can't do that, right? What do you have to do with the error? You gotta do something with it. Now, it turns out this will help us discover what you have to do with it. It's not at all obvious at first. So what I did was I made up two different distributions, x1 and x2. This is randomized, so if I press F9, I get different values. Okay, get a little dance going on. The yellow one here is the x1 distribution, and the blue one over here is the x2. Notice they're very different from each other, kind of like my brakes. You know, I got the V brakes, and you got the cantilevers over here. So very different from each other. You get different samples of my brakes being taken. Different samples of my brakes being taken. It's not bell-shaped, but that's okay. What I did in green was I subtracted x1 minus x2. Now take a look. Take a look. The average of x1 is 26. The average of x2 is 76. The average of the distribution is negative 50. That hopefully makes perfect sense. You're subtracting x1 minus x2. So if you subtract x bar 1 minus x bar 2, you get the average difference between them of negative 50. Is that believable? Partially believable. Hopefully that's believable. And that stays consistent. There's definitely experimental error involved, but you see every once in a while they fluctuate a little bit. But still, nonetheless, the average difference in the averages is staying the difference of these two. Brian, go.
Well, couldn't you use the average in the single U formula?
The problem is, yes, if we had a value for this.
Right.
That's the, right, it all goes back to you have to be able to plug things into each of these things. And that's the problem. And we still don't know what the hell this is. We still don't know what S is. Oh, I just turned the camera. Sorry, the camera's pointing at the wrong thing. There we go. Thank you for that, Brian. This is good. This is good. So, what I did then was, I calculated the variances of each of the distributions up here. Now, it turns out they're about 208 each. And then I calculated the variance of the difference of them. How is 416 related to the 208s?
Them added together.
Uh-huh. It's them added together. And then what I did behind these two graphs is I graphed the average sampling distribution of the differences. Did you notice how the green distribution spans all the way from the leftmost point of the yellow all the way to the rightmost point of the blue? It's twice as wide. Now think about the example I gave you with Brandon a minute ago. Brandon's off by ½ an inch, Sean's off by ½ an inch. If we have them both measuring on a job site, how much are they going to be off by on average? Probably we could expect about 1 inch of deviation because his ½ an inch and my ½ of an inch compound on each other. What you're seeing here is the exact same idea. Standard error compounds, it doesn't subtract. You don't lose error when you put stuff together, you gain more error. Does that make sense? This is why when you're building something, if you guys are building something out of wood, here's one way to not cut foot lengths off of a 2x4. Take your ruler, put it on the end, stretch it out 10 feet, and go a foot, a foot, a foot, a foot, and then start cutting those lines. Don't do that. Why? Every time you cut with a saw, you have a kerf that takes a little tiny bit of wood off, number one. And every time you cut, you're off a little tiny bit anyway. Even if you do it as perfectly as you can, you're still off. So the first one you cut, you're a little bit off and you lost the 1/16 of an inch. Then you come down a little bit further, you're a little bit off and you're already off because you lost the 1/16 of an inch. So you're compounding your error with each additional measurement that you make. So right here, we took 2 measurements. The error can't be subtracted, it has to be added. It has to be added together. Now, as it turns out, if you ever need this, and I doubt very much anybody ever will, the actual formula looks like this. And honestly, I don't think anybody would ever need this. It depends on who you take stat with next, if you take stat with anybody. I'm never going to make you calculate this. This is the errors added together correctly. And the reason is, these have had the square roots taken of them already. If you have to add them correctly together, you have to first add the unsquare rooted versions and then take the square root. I doubt very much anybody sitting in this room will ever have to do that. But all that is the algebraic representation of what you're seeing up here. Added variances. Added variances. That's it. That's it. I will never ask you to do that manually. And hopefully nobody else ever does either. I swear, I'm crossing my fingers on my toes right now. Because it's too tough to do, number one. And number two, once you have that, you still have this degrees of freedom argument that you have to deal with a t-distribution, which is another nightmare of epic proportions. So the basic thing you want to know how to do is what to do with this data. We know we have to run a t-test, and we know we have to run a t-test on 2 samples. That's all you got to, once you know that, you know what software to run. With me? Okay, turn Excel off. I feel like it's giving you a headache. Turn Excel off. Go back to your machines. Let's figure out what tests we're going to run. Let's figure out what tests we're going to run. Fire up. Stat. Tests. We ran this guy before. Simple t-test. Take a guess who we're going to run next. That guy right there, number 4, 2 sample t-tests. He's the one. It's going to look extraordinarily similar to a t-test with one thing definitely missing, which I find very, very fun. First of all, do we have data or do we have statistics? Data. We've got data. Make sure you put your stuff in correctly here. List 1, list 2, freak 1, freak 2. We've got 2 sets of raw data. So our data is, oops, hit the wrong button. Our data is in L1 and in L2, for sure. L1's V-brakes, L2 is cantilevers. What are the frequencies on those? Be brave. 1. 1 each, because they're raw data. This is why I couldn't do that graph earlier with the scatter plot, because they're raw data. Now just carefully choose the right sign. What is mu1 compared to mu2? Well, according to our claim, it's less than. So we drop that sign in there.
Yes.
This one you will always leave on no. I'm not even sure why it's there anymore. Pulling variances is assuming that your 2 samples have the same variance. The reason why that option is still there is because back when everybody did these by hand, back in the day, it was easier mathematically to assume samples had the same variance than if they were different. And the mathematics is much simpler. But now that we have technology, it's like, why? There's no reason to assume that they're equal if they're not. So never pull them, just leave it on no. There's absolutely no good reason to ever pull a variance. Go down a little bit further. Brian, ask me that question if you have one. I'm sorry, did you have a question?
Oh no, I was just thinking about how they're off.
Well, the thing is, we don't know they're off, but this will force them not to be off if they are. It will take an average variance, which I don't think is a good idea. I mean, if you have different variances, it takes a weighted average of the variances, which it's easier just to let them be what they are, so to speak. All right, here we go. It comes down to a single curve. Here it comes. It's going to take its sweet little time. Okay. Excuse me. After I got done telling you guys to make sure you pick the correct... Oh, I did pick the right sign. mu1 less than mu2. I got them labeled wrong up there. I put mu1 is my V-brakes and mu2 is my, but I put them in the TI backwards. I put, this is the cantilevers in the TI. This is the V-brakes. And when we defined the variables, we switched them around. Did you catch that? Because now the reason I stopped and I said, excuse me, was I saw something that was disagreeing with what I was expecting. You guys have already decided that the V-brakes are better than the cantilever brakes, right? So let me go back. Let me go back and let it finish what it was doing. As soon as it started doing its calculation, I started seeing an awful lot of area showing up. Area equals what? What part of the hypothesis test is the area showing you? Of the 10 steps here, what is the area showing you?
The variance between,
But what is it called? The amount that's shaded is the p-value, right? When something is significantly different than something else, what kind of p-value do you get? Less than 5%, small, right? When I saw the area coming in, there was a lot of area coming in. And I thought to myself, it can't be that, right? It can't be that if the V-brakes were actually doing a better job than the cantilevers. I shouldn't see that much area at all, should I? And then as I saw it getting close to half, I'm like, okay, I put something in wrong. So I stopped it. And then went back and looked, and I was like, no, mu1's less than mu2. But I forgot. When I put the data into my TIs, I put the cantilevers in L1 and the V-brakes in L2. And then when I asked you guys to define the variables, you defined mu1 to be the V-brakes and mu2 to be the cantilevers. We defined them differently than we entered them. Does that make sense? So technically speaking, we have to switch something. Whether it's what we define the variables to be, which I'd rather not do. I'd rather just leave those the way they are. Let's just switch the list to the TI, if that's okay with you guys. Okay? It's easier to do it this way. So everybody see what's going on here? I have to take my lists and make them backwards. L2 and L1. Right? List 1 is actually going to be list 2. Now, list 1, which is tied to mu1, is my V-brake distances. And list 2, which is tied to L1, is my cantilever brake, and now it's going to shade exactly the opposite of what it just shaded. Does everybody see the problem we had right there? That was kind of fun, actually. That was a good problem solved. Chris?
What would happen if you were to just switch the...
This sign?
Yes.
Nothing! Nothing at all. It would be the exact same thing. The reason I'm doing this is because we're testing less than, and I'm trying to keep this looking as much as what you guys just wrote down as possible. And the easiest thing to do is just tell the TI to switch the two lists.
Okay, so if you were to...
No problem at all.
It would have been
exactly the same thing. Exactly. Now the reason, you'll see again why I'm about to show, there's a second reason that's a little bit more statistical, not as logical, a little more statistical. That's the wrong phrase to use, but you'll see here in a second. Okay, here we go. Let's draw it. Okay, no area, no area. This is what I was expecting. But the p-value that we just had came in at 1, which is 100%. This p-value is going to come in at 0, which is the complement of that. It went the other way. And you're going to see it here in a second. Here's the reason right here, Chris. See how that's negative? If I just switch the sign, it would be positive. Somebody misreading your hypotheses is going to think, therefore, that the cantilevers are significant over the V-brakes versus the other way around. That's super negative, isn't it? That's super negative. 12 standard deviations less. That's ridiculous. Like, completely freaking ridiculous. And the reason I like that better is because the negativeness means that x bar 1 is that much smaller than x bar 2, which means the average stopping distance of the V-brakes is that much less standard deviation-wise than the average stopping distance of the cantilevers. That's the only reason. I was trying to keep your test intact. I should have paid closer attention when we were defining the variables. I should have just said, oh, we're going to make mu1 be cantilevers and make mu2 be the V-brakes. So yeah, now we can publish our results and say, here we go. Scientific proof that the brakes are stopping better. Have somebody replicate it without a 7-year-old or a 6-year-old helping. That might be a good thing too. So we got ourselves a test statistic. T is negative 12.6. We got a p-value, essentially 0. It's not really 0. It's not really 0. And what you're looking at too, friends, I'm going to put this up for a second so I can draw the board. What you're also looking at right here, what you're looking at, this would imply 0 difference between the two brakes. If our test statistic landed up here somewhere, that would actually mean that the cantilevers were doing better than the V-brakes. The further it moves to the right, this is cantilevers better. And as we get this way, that means the V's are doing better. The V brakes are doing better. Where we ended up was way the hell over here. That's significant evidence that the V brakes are doing much better than the cantilevers. We're nowhere near the original curve at this point. That's kind of cool. Believable? I want to go back to a question Brian asked. Why not just make 2 confidence intervals? Stopping distance for the cantilevers, stopping distance for the V's, and see if they overlap. Why not just do that? That seems like a much simpler solution, right? I would think. Say that again. The beauty of doing it that way is you wouldn't need a reference point. I mean, you wouldn't need one because you could simply just say, whatever the reference point is here, let's see if the cantilevers come on this side of it or this side of it. In other words, if they don't overlap, that means even at the slowest braking of a V brake, it still brakes quicker than the best stopping distance of a cantilever. I like what you said about the reference point. That's only if we're comparing it to some UCI standard, like you have to stop within 20 feet. But if all you're trying to show is that the cantilevers are better than the V's, why not just make 2 confidence intervals and go like this? It's an old reason. I haven't asked this in a couple weeks. What do you lose by doing that?
All the other points, right? Because we only look at.
Oh, well, but I like that too,
Yeah.
but you're also losing that with this test, theoretically, because we're just doing the average of all the data sets. It's an old question. It's a Bastian question, actually. What do you lose when you do repeated confidence intervals? I just gave you the answer. You lose confidence. You're no longer testing at 95%. If you keep slapping confidence intervals down, you keep losing confidence. That's part of the problem of it, is if you keep running intervals. Now, there is something, you may have noticed it in your TI. I'll mention it now, I'll never mention it again. Because you might see these in your literature that you're consuming. Whoops. If you go to the stat tests, there's a thing down here called a 2-SAMP-T interval. That's the same thing as a hypothesis test, but instead of doing a hypothesis test, it actually constructs the interval of the average difference. Now, so you select this one, it looks exactly the same as the test you just ran. It looks exactly the same as the test you just ran, except down here it asks for a confidence level, which is what you guys were used to doing back when the course started, back when you still liked it. And if you go down to calculate this, notice what number, it's going to take a while to calculate it. Notice what number it doesn't contain. Negative 7.7 to negative 5.6, or negative 7.6 to negative 5.6. What number doesn't it contain? What very important number doesn't it contain? You're thinking too specifically. Look, what number is not in this interval? 0. Why is that significant? This, FYI, this is the number of feet less braking it takes for the V brakes over the cantilevers. So it might be as many as 7.8 feet less, or it might be as little as 5.6 feet less. Why is 0 not being in there significant?
Doesn't give you a reference.
Yeah, less than 1.
Say that again, Chris.
Doesn't give you a reference as to how much better it is.
That's what this exactly is. It says that the V brakes give you at least 5.6 more feet of stopping, maybe as many as 7.8 feet of stopping. So that's all the reference you need. Suppose 0 was in there. Suppose the interval went from negative 7.8 to positive 5.6. What couldn't you tell then? If there was a difference, I'm asking a question from like 5 weeks ago. This is why it's hard for you, because you're like, wait a minute, I'm not quite following this. This is from a long time ago. It is from a long time ago. If the 0 was in the interval, that means you couldn't tell which one was better. Fishing back and forth. If it was a positive number, that means the cantilevers are doing better than the V's. If it was a negative number, that means the V's are doing better than the cantilevers. And if it's 0, that means they're the same. You can't tell which is better in that respect. Fair enough? The thing about this is, you can totally tell which one, 95% confidence anyway, you can totally tell which one's doing better. The V brakes are doing better because all the numbers are negative. Is that believable? So this is a way of giving you an estimate of how much better the brakes are doing. But just so you know, you'll see these out in the research sometime. Right, ask me that question. Ask me that question. No.
No,
Just processing.
right.
Maybe,
Well,
okay.
It's only giving you a section of the information.
And it's based on my sample data, isn't it? Right? This is entirely based on my sample data. If you ran this experiment again 20 and 20 times, I'm not saying it's going to come up the exact same. I'm saying it's 95% likely to come up similar to that, though, assuming my data was good. And that's the idea also of that t-test you guys just ran. That t-test back here that you just ran, this 2-sample t. That negative 12.6 p-value, or test statistic you got down here, you won't see that again in a second study. But you're most likely, if my experiment was done properly, going to see something similar to it. Now, it's possible that my data is completely screwed up, and I got a ridiculous outlier. Maybe I was braking different on day 2 with the V-brakes, and I just braked better that day. What I should have done was randomized which brakes I used which. I did the entire thing with the cantilevers, and then once I installed the V-brakes, I did the entire test again. It's possible, of course, that I learned from braking the first time around, but I would throw that out with the bathwater, so to speak, because honestly, I've been riding a bike for so long, I brake pretty much the same. I didn't change my braking because of the new brakes. I did skid that one time. Which was because the brakes were grabbing so much, they locked the wheel up that one time. So that one, we can throw that out as an outlier if you wanted to. I don't think it's going to make that much of a difference, though. Please!
What is P? We can't read it from back here.
Oh, it's 0. It's saying 0, Tracy, although it's not. It's just extraordinarily small. There we go.
Oh, thank you.
Yep, no, thank you. It's an extraordinarily small number. Extraordinarily significant difference in that respect. So now you can publish your results versus just anecdotally telling your buddies to go out and spend a lot of money on brakes. That's the point, if you can stand up to scientific scrutiny. Cool? You guys look completely flogged. It's okay, it's totally understandable. It's not the simplest thing to do. Although, hopefully, you now know which tool to run. You simply run a 2-sample t-test. That's what you do with these 2 samples of data. 2-sample t-test.
So how small of a p-value would the TI list? So like if it was 1...
.000, well, you know, I take that back. Probably scientific notation-wise, I'm not sure what would fit in this little space here, Brandon, but I think if it's scientific notation, technically speaking, it can show out to like 10 to the negative 99th power, which is ludicrous. I mean, that's 98 zeros and a 1. So you can see how small this actually is. You're so far in the tails, it's pinched down almost to nothing. That makes sense?
So, but it wouldn't show in scientific notation there, would it?
That's the question. I don't know if it would or not. Like, I don't know how significant that difference has to be to make... I don't know if it can actually display that many scientific notation digits here.
Yeah.
I've seen it say things like 1e negative 8, which is times 10 to the negative 8th.
Okay.
I just don't know if it'll do a 2-digit scientific. So at least 10 to the negative 9th.
Okay.
Maybe even less. Or I guess at most. Maybe even less. Is that fair?
Mm-hmm.
Yeah. And Excel deals with that. A publication would deal with this by simply saying it's equal to 0. P approximately equal to 0, which it essentially is. Did everybody catch I want to make sure this was clear, because it was a fun little learning moment for me to pay closer attention to how we define the variables. Why we got that p-value of 1 about 10 minutes ago when we ran the technology. Everybody seeing what happened there? That was good. I should have just let it go and then just not interrupted it, let it go, and then asked you about it. But that's why it's so important. Technology does all this stuff. But we have to know when it makes sense. And that's why I like the fact that we looked at the data first and we had a theory. Our theory was that the V-brakes were doing better. This tells us they're doing significantly better. But that p-value could not have been right. There's no way that p-value could have been as big as they were because we knew the V-brakes were braking less than the cantilevers. That's the kind of stuff you guys need to check when you read research models. People don't do the correct math all the time. They'll do the wrong math sometimes. You have to be paying attention to that. I heard spinach cooked is actually worse for you than spinach uncooked. One of my students actually told me that 2 years ago. What? Yeah, if you eat raw spinach, it's worse for you than cooked spinach. Where did you read that? Oh, it was this article. Send me the article. All anecdote. Full of anecdote. Full of anecdote, not one proper statistical method done. That's the problem with the world we live in. Information overload with absolutely nothing backing it up. Airborne, perfect example of that. Airborne, cold remedy, fizzily airborne, right? Shown, clinically shown to reduce, I forget the claim now, it's been years since they stopped printing it. because they discovered that the claim they had was based off of one study paid for by the company that makes airborne. Well, it's a slight problem to do that kind of stuff, right? But even if you look at the study itself, it was such a small sample done one time without replication, the significance they were claiming wasn't even there. Essentially what they were saying was, take airborne and your cold will be gone in 7 to 10 days. Or sit around and your cold will be gone in 7 to 10 days, because that's how long colds usually last. See what I'm getting at, friends? Made by a second grade teacher. I mean, I fell for that too. I'm like, that's brilliant. Second grade teachers surrounded by germs all the time. Wait a minute, they have no medical training though. Why would they be justified in making a drug? And then when you start thinking about it, you're like, oh God, rule, you fell for it too. But it's convincing, it's marketing, that's what they're paid to do. Their marketers are geniuses. But check their math every time. Check their math every time. You now have another technique for checking math. But not anymore, because you, like I said, you look exhausted right now. So here's what I want you to do. Between now and next time, if you want to look at, now you gotta do between now and next time, don't you? Oh shit, I don't see you on Thursday. Okay, no, I don't see you guys until Tuesday. I'm gonna put something in your mind here. Don't think about this till after you do your project though. Look at this ADD, non-ADD data. You see right here? It's right after it's on your data sheet. Do children diagnosed with ADHD have smaller brain volume than those without ADHD? Being ADHD myself, this was interesting to me.
Of course they do.
Well, look at the data.
They're all small pinheads.
Look at the data. Mr. Anecdote back there. Look at the data. We got ADHD kids, 152. Non-ADHD kids, 139. Do they have smaller brain volumes? Simple answer, yes or no? Yes, based on this sample, the brain volume of an ADHD kid is 1,059.4 milliliters. The brain volume of a non-ADHD kid is 1,104.5 milliliters. That is smaller, yes?
Is that fluid?
It's
What do you fill them with, like beer or something?
it's an equivalent fluid mass, I'm assuming. I mean, they measure it in milliliters. I'm assuming it's some kind of sonogram that they use to measure the brain. I'm just filled with beer.
Okay.
I'm assuming that's what they do. I mean, I pulled this out of the American Medical Association's journal. I don't know. I mean, I'm trusting they can measure a brain properly. Yeah, I'm guessing they pick a fluid like water and they figure out what volume would contain that many milliliters of water, and that's how big the brain is on average.
Crazy.
Yeah, I mean, how else would you measure it though?
Is it?
How else would you measure a brain volume?
That seems right.
Why would
Milliliters, right? Because volume's length times width times cubic centimeters. You could do it with that. But a cubic centimeter of water is the same as a milliliter. So therefore, just change it to cc's and call it good. There. Chris, change the unit to cc's and it's the same thing. Same number. A cubic centimeter is a milliliter in the metric system. So just make it cubic centimeters. But the question is, are they smaller?
So they're saying that they have smaller brains.
The sample says the sample data is smaller. The question therefore is that significant across the population? Is that significant across the population? We'll start with this one next time, because I don't want to do it in 10 minutes. But take a look at it. You could probably knock this one out yourself in literally 10 minutes. We can treat this one as an in-class quiz if you want next time. Cool? So yes for the sample, question mark for the population. Is it replicable for the population? Have a good Thanksgiving, you guys. Take care. No, keep those. I want you to keep those for reference, yeah. I don't like to take